If we remove the empty space in atoms, all of humanity could be reduced to the size of a sugar cube. You can't see or feel them, yet everything, everywhere around you is built from atoms. But have you ever wondered what happens when truly atoms go out of control? How can something invisible turn into a force powerful enough to power entire cities or wipe them out in seconds? But first, let's understand what is inside an atom. Why is it so powerful? There are three fundamental particles that make up an atom: electrons, protons, and neutrons. But this simple breakdown is far stranger than it sounds. The idea of atoms goes back over 2,000 years to a Greek thinker named Democritus, who believed everything could be broken down into tiny, indivisible pieces. He called them atomos, which means uncuttable. Well, and he wasn't completely wrong, but atoms aren't actually indivisible. At the center of every atom is its nucleus, and this is where everything important comes from. The number of protons sitting there decides what the atom actually is. 1 proton gives hydrogen, 8 gives oxygen, and 92 uranium. If you change that number, you're dealing with a completely different element. Now here's where the power really comes in. That nucleus is incredibly small, but it holds almost all the mass of the atom. The particles inside it are bound together by the strong nuclear force, which is far more powerful than gravity, but only works over super short distances. It has to be that strong, because protons naturally repel each other. Outside the nucleus, electrons exist in specific energy levels. When they move between those levels, then they release exact amounts of energy, and that's how atoms interact, bond, and build everything around you. But almost all of the atom itself, we mean about 99.9%, is empty space. So what looks simple on the outside is actually a tightly balanced system, where an incredibly small center holds an enormous amount of energy. What happens when that balance breaks inside the nucleus? We know that an atom is many thousands of times bigger than its own nucleus. But have you ever thought about what keeps that tiny center from falling apart? Well, at that scale, things don't behave the way we expect. Protons all carry the same positive charge, which means they should push away from each other immediately. But somehow, they stay locked together. The reason is the strong nuclear force, a force so powerful that, within an extremely small distance, it overcomes that repulsion and keeps the nucleus intact. But that balance is delicate. As more protons are added, especially in heavier elements, that internal push grows stronger. Neutrons play a quiet but critical role here. They don't carry a charge, so they don't add to the repulsion, but they do strengthen the nuclear binding. That's why heavier atoms need more neutrons than protons just to hold together. Once that ratio shifts too far, either too many neutrons or too few, the nucleus starts losing stability. There's also something called binding energy. This is the energy holding the nucleus together. And let's say, the higher it is, the more stable the atom. Elements like iron sit at a point where this binding is strongest. But beyond that, especially in very heavy elements like uranium, the structure becomes harder to maintain. The nucleus carries excess energy. It can't hold forever, so it begins to change. That change doesn't happen all at once. The nucleus starts releasing small pieces of itself, sometimes ejecting a cluster of particles, sending out a fast-moving electron, or releasing pure energy in the form of gamma radiation. Each step slightly reshapes the nucleus, shifting it toward a more stable arrangement. This process is called radioactive decay. It doesn't happen on a fixed schedule for a single atom. It's random at that level. But across large numbers, it follows clear patterns, measured through something called half-life, and it doesn't always end in one step. Some atoms go through entire decay chains, transforming again and again until they finally reach a stable state. And so when that balance inside the nucleus breaks, what follows isn't instant hell. It's a controlled release of energy, one step at a time, as the atom tries to settle into something it can hold together. How a single atomic split starts a chain reaction. Once upon a time, early scientists and philosophers thought that an atom was uncuttable and could not be split. But that belief didn't last long once experiments proved otherwise. By 1938, scientists had already shown that when a neutron hits a heavy atom like uranium, the nucleus doesn't just absorb it, it becomes unstable and splits into two smaller atoms. In that split, it doesn't divide evenly. One atom might turn into barium, another into krypton. Along with that, energy is released. But the real turning point isn't the split itself, it's what comes out with it. A few extra neutrons are thrown free in that same moment, and those neutrons don't just drift away. They move outward and strike other nearby atoms. If those atoms are in the right condition, they split too, and when they do, they release more neutrons. That's where things start changing. One reaction becomes several become dozens, and in a fraction of a second, it begins multiplying faster than anything you can physically track. This isn't a slow process you can step back from. It's a rapid chain, where each step triggers the next almost instantly. Under controlled conditions, this can be managed and slowed down. But if nothing absorbs those extra neutrons, the process keeps feeding itself. And once it crosses that point, it doesn't settle down again. When the chain reaction gets out of control. Now, and this is one of the most destructive things you can deal with, because once a chain reaction crosses a certain point, there's no slowing it down in time. That possibility became clear not long after the breakthrough of 1938, when Otto Hahn, Lise Meitner, and Fritz Strassmann revealed that a uranium nucleus could be split by neutrons. What made the discovery truly frightening was what Leo Szilard understood right away. If one fission event released neutrons, and those neutrons could split more uranium nuclei, then the process could keep going by itself. That idea was proven on December 2, 1942, at the University of Chicago, when Enrico Fermi, Szilard, and their team built Chicago Pile 1, the world's first controlled nuclear reactor. It measured roughly 20 by 6 by 25 feet and was made from uranium and graphite. The graphite slowed fast neutrons down because uranium absorbs slower neutrons more easily. Cadmium control rods were inserted throughout the pile because cadmium absorbs neutrons well. Fermi's team knew the line was razor thin. Too few neutrons and the reaction would die. Too many and it could run away. That is exactly what out of control means in nuclear terms. A reaction becomes supercritical when more than one neutron from each fission keeps triggering another split. Then it does not move step by step, it accelerates. In uranium-235 or plutonium-239, each fission can release 2 or 3 neutrons, and when those neutrons are trapped inside a compact mass, the number of fissions rises brutally fast. In an atomic weapon, that burst happens in such a tiny fraction of time that there is no meaningful chance to stop it. Inside a reactor, the disaster takes a different form but follows the same logic. Excess fission produces excess heat. Fuel can rise above 2,000 degrees Celsius, melt into corium, and damage the reactor vessel. If molten fuel meets coolant, steam explosions can follow. If hot zirconium cladding reacts with steam, hydrogen gas forms, which can ignite or explode, exactly what happened at Fukushima in 2011 after the tsunami knocked out cooling systems. At Chernobyl in 1986, the chain reaction surged in a dangerously unstable reactor. A steam explosion tore apart Reactor 4, followed by fires and a massive release of radioactive material that still lingers there. So when the chain reaction gets out of control, It is never just one event. It becomes blast, fire, radiation, meltdown, and fallout all at once. Atomic reaction and its effect on life. Well, when according to scientists, Chernobyl is still not a place where people can live normally, and in some areas, it won't be for tens of thousands of years. Not because the reactor is still burning, but because of what was scattered after it broke apart. On the night of April 26th, when Reactor 4 exploded, the damage didn't stay inside the plant. The explosion and the fires that followed pushed radioactive material high into the atmosphere. For about 10 days, it kept leaking out, carried by the wind across Ukraine, Belarus, Russia, and even parts of Europe. The town of Pripyat, which is just 3 kilometers away, had nearly 49,000 people living in it. They weren't told immediately what had happened. Life went on for hours like nothing was wrong. By the next day, buses arrived, and the entire city was evacuated. Within weeks, around 116,000 people were moved out of the surrounding area, and later, that number reached about 350,000. The people closest to the reactor felt it first. Firefighters and plant workers went in without knowing the level of exposure they were facing. Within weeks, 28 of them died from acute radiation syndrome. Some had received doses so high that their bodies couldn't recover, like burns, organ failure, internal damage that didn't stop. But what made it worse was what didn't disappear. The land itself changed. Soil, forests, rivers, and everything in the area carried contamination. Farmers couldn't trust crops. Milk had to be tested. Entire villages were abandoned, not because buildings were destroyed, but because living there meant constant risk. Years later, doctors started noticing patterns. Their kids who had been exposed were showing higher rates of thyroid cancer, linked to what they had taken into their bodies right after the accident. It didn't hit everyone the same way, and it didn't show up immediately, but it was there. Japan faced a different version of this in 2011, when the Fukushima Daiichi plant lost power after a tsunami. The reactors didn't explode like Chernobyl, but the cooling systems failed. Fuel overheated, and 3 reactors melted down. Hydrogen explosions followed. More than 150,000 people had to leave their homes, many of them never returning because no one could promise it was safe. So the effect on life is never just one thing. It is physical, environmental, social, and psychological all at once. It can kill in minutes, contaminate for decades, uproot hundreds of thousands of people, poison food chains, send empty cities, and leave behind fear strong enough to shape generations. That is the true human cost of atomic reactions when control is lost. Well, that's all from us. Thanks for watching, and be sure to like and subscribe. We'll see you soon.